Okay. All right, let's go ahead and we're now going to talk about, we're going to do some problems with the mean value theorem. But instead of doing problems from the textbook, I'm actually going to show you a couple, we're going to do 3 AP exam free response problems. We're not going to do the whole thing, we're just going to do pieces of them. We're going to do pieces that include the mean value theorem. Okay? Before we do this first one though, I need to tell you that starting, not really, kind of starting today, one of the videos that you have to watch tonight is on how to identify zeros with a graphing calculator. For the until Thanksgiving, you guys are going to need to be bringing your graphing calculators every day. In fact, they're good. Is it in there? Good. We are going to use the graphing calculators on quizzes. And yes, that is good. And yeah, yeah.
How much you on every quiz?
Okay, so you won't be able to.
I'm kidding.
Yeah.
I wouldn't do that.
Yeah.
It still wouldn't even work. Like I'd probably still fail. I'd feel worse, honestly.
I don't think so.
Okay. Can I ask you questions about that right now?
From the
It's from the textbook.
yeah, exercises from the textbook.
Well, it was actually one of the examples they showed.
Okay. Yeah. You know what? Why don't you go ahead and ask that now?
Okay. So it was actually example 1.
Example number 1,
Yes.
which is on page.
Oh, I don't have page number.
That's okay. I got it. Example 1 starts on page 196 and goes through to 197. Yep.
Value theorem.
Exploring the mean value theorem. Yep.
So, okay, like I understood like everything with the plug-in
Yes.
and all, but then towards like the end, it
Yes.
said 2c equals 4 minus 0 over 2 minus 0. Or f. Like do you see
F prime of C.
f prime c, and then do you see where it says like 2c?
I see 2C equals F of 2 minus F of 0. 2C is the derivative of x squared. It's saying, yeah, it's saying that the instantaneous rate of change, the derivative, at some point is equal to the average rate of change. Do you really?
Yeah,
That's
I
cool.
think my problem is just finding the critical points. It's so hard.
Oh, sure, yeah. Now you should know, for the extreme value theorem?
Yeah,
Well, the calculator is going to make that a lot easier.
Yeah.
Because on the AP exam, probably a good half of the questions where you have to find critical points, you're doing so with a calculator.
Yeah.
And when I show you how to do it with the calculator, actually, I'm not even going to show you how to do it with the calculator. I will expect that you have watched the video that I've assigned for tonight, which is about a 3-minute video that shows you how to identify zeros with a graphing calculator. See, the problem, the reason you can't, hang on one second, Ace, the reason you can't really cheat is even though you can find the zeros, you still have to be able to find the derivative. You still have to be able to identify the derivative, which is not that easy to do with a calculator. You can do it with a calculator, but it's not that easy to do. Also, if you have to find a derivative on the AP exam, if it's a free response question, they expect you to write out the derivative. Okay, not in all cases, but in many cases. If it's a calculator question, not so much. But in other cases, they expect you to write out the derivative. Yes, ma'am?
Yeah, when I was looking at the answers online,
Yes.
for extreme value theorem, they would show you like a graph.
Yes.
And I was like,
Not a graph, a table.
No, I'm talking about.
Oh, they show the graph on the calculator. Yes, sure.
I didn't know how to do that only do algebra.
Sure. Well, what you could do is you could that's the right way to do it with algebra. But you can use the graphing calculator to validate your answer. If you bring that information in, guys, you can come in and see me in the morning with any question about calculus. Okay? It can be, hey, how come in the solutions manual they show this graph thing and then these are the answers? Why are they doing this? I don't understand it. I can decipher it for you. Okay? So I feel like not enough people come to me with questions. For the grades that people are getting in this class, not enough people are coming to me with questions about things that they don't understand. You come to me more than anybody else. Okay? But I feel like people are not coming to me as frequently as they probably should be. All right, here's what we're going to do. This is from the 2007 AP exam, and you can access this stuff online. If you go to the AP Central or just Google AP Calculus free response questions or something like that, there's a page it's called AP Central, where you can get old questions. In fact, they post the free response questions 48 hours after the exam is given. So you'll take the test on Tuesday, I'll get the free response questions by Thursday afternoon. And then I can start solving them right then and there.
Are these
Okay?
questions the mean value theorem?
The ones I'm showing you are going to be related to the mean value theorem.
Okay.
The one we're doing right now is from the year 2007, and back in that day they did what is called a Form B. Form B was like an alternative form that they would give for like either if the test was given late or the test was given under weird circumstances, they would use Form B. Okay? So 2007, Form B, question number 6. This is what we say, AB, meaning it's the AB exam, question number 6, AB 6, free response question. And we are going to do parts A and B. We're going to do parts A and B. Okay, so if you look up there, first you have the stem of the question. Let f be a twice differentiable function. That just simply means that it has two derivatives. And that it has and that f is a differentiable function and f prime of x is a differentiable function. It is twice differentiable. Okay? Let f be a twice differentiable function such that f of 2 is equal to 5. F of 2 is equal to 5 and f of 5 is equal to 2. Easy enough. This is a numerical question. No graph, no function, just numerical values. Let g be the function given by g of x is equal to f of x. It is a composition function. Okay? F of x. So you would take f of x and plug it into the x in f of x, and that would give you g of x. G of x is also twice differentiable. How do we know that? Because it is a composition of functions that are twice differentiable. You may not remember that from when we did the chain rule, or when we did, differentiability, but composition functions. If two functions are differentiable and you do a composition of those functions, the composition itself is also differentiable. You may or may not remember that, but you got to go back to 4.2.
Is that like one
Yeah.
of those things, like you know how when you multiply two negatives there's a positive? So if you do two undifferentiable equations, would the next one be different?
No. In fact, if you plug a differentiable function, if you do a composition of a differentiable and a not differentiable, the whole thing is not differentiable. Yeah. Think about what's causing it to be not differentiable. It's a rational function, so it has a vertical asymptote, or it has a jump now it could become, I'm sure there's some circumstance under which you plug a differentiable function into a piecewise function that had a jump and now it doesn't have a jump anymore. Maybe. Okay? All right, so part A says, explain why there must be a value c on the open interval from 2 to 5, such that f prime of c is equal to -1. What does that mean, f prime of c is equal to -1?
The derivative of f at
Yeah, the derivative of f at c is equal to -1, right? Is there another way to say that? No. Let's think of 3 ways of saying this. Not average rate of change.
y over gx.
What's the other one? Not average rate of change. The
slope of c is
okay, the slope of f. No, yeah, the slope of f of x at c is -1. You gotta get those things right. C does not have a slope. C is an x value. Okay? The slope of f at c is -1. Okay? Now, you were on to something there, Elizabeth. You said average rate of change, and I said, no, wait, not average rate of change. What's the other one?
or instantaneous rate of change.
Instantaneous rate of change. The instantaneous rate of change in f of x at c is -1. Let me give you one more. The slope of the line tangent to the graph of f of x at c is -1. Did you understand what I just said? The slope of the line tangent to the graph is -1. And that, since we're talking about slope of line tangent to the graph, some of you guys, Keanu, you especially, but a couple other people, there have been several times I've asked you for the slope of a line tangent to the graph, and you give me the equation of the line. I don't want the equation. I just want the slope. If I say give me the equation, give me the equation. But if I just want the slope of the line, just give me the slope, please. Okay? Okay, so what is the... This is a mean value theorem problem. Cat's out of the bag. Now, when you're taking the AP exam, it doesn't tell you it's a mean value problem. Mean value theorem problem. How do we know it's a mean value theorem problem? Is there any other theorem that guarantees a slope? No. The mean value theorem is the one that guarantees a slope. This is guaranteeing a slope on f of x at c of -1. How does the mean value theorem guarantee a slope?
Because it's continuous and differentiable.
Has to be continuous on the closed interval, has to be differentiable on the open interval.
But that's not a closed interval.
Right, but here's the thing. It's asking about the open interval from 2 to 5. So now you have to ask yourself, is it continuous on the closed interval from 2 to 5? How do we know that it's continuous on the closed interval from 2 to 5?
Because it's twice differentiable.
Because it's twice differentiable. That's exactly right. It says, let f be a twice differentiable function.
Wait, so what is twice differentiable?
It means that it has it means that the original function is differentiable at all points, and that the first derivative is differentiable at all points. That's twice differentiable. You'll see the phrase twice differentiable. All that means is that it has a first derivative and it has a second derivative. Okay? Yes. Did you have a question?
No, I said oh.
Oh, okay. All right, so what would have to be true in order for this to be true? Okay, we got that. We're good. It's continuous and differentiable. Maybe we even write that down.
Closed interval.
Okay, wrote that down.
Well,
What is the therefore, or what is the then? If it's continuous, if it's differentiable, then
then the FB minus FA over B minus A is equal.
average rate of change. In order for the mean value theorem to apply, we have to have an average rate of change. That's what?
-1.
We have to have an average rate of change of -1. On what interval?
2 to 5.
2 to 5. So how would we write the average rate of change from 2 to 5? Instead of using B and A.
So
F of 5 minus F of 2 over 5 minus 2, which is 3. Okay?
would be
Equals -1.
2 minus 5 over 3,
So it'd be
-1.
-1.
Ooh, look at that.
So now, must there be some point on the interval? On this interval, 2 to 5. Does there have to be a point somewhere in there, a C value, where the actual slope, where the instantaneous rate of change is -1? Yes, has to happen. Okay?
That question was easier than the other questions.
Oh.
The AP one was.
That one, I think that that's going to be true. I think when you take the AP exam, you're going to say that those questions were easier than the ones you gave me, Mr. Ryan. Yes. Yeah.
I'd rather it be
What's that?
I'd rather this class be harder than the
Yes, and that's the way, I believe that's the way it should be. Okay? All right, now let's look at the next part. Let's look at part B, and we're not going to go to C and D. Although we could look at them. Actually, look at part D. Let h of x equal f of x minus x. Explain why there must be a value r on the interval from 2 to 5 such that h of r equals 0. What do you think you would use for that?
Here's what would that be intermediate?
Intermediate value theorem.
But how would you do that?
Uh,
What is
identify f of, well, the interval's from 2 to 5, so we would need an f of 2, or an h of 2. We'd need an h of 2, and we would need an h of 5. And 0 would have to be between them.
Oh, I'm so
Sorry, that's an intermediate value theorem problem right there. All right? So there's a perfect example of an intermediate value theorem problem. Not all that different than what I gave you when you took that quiz. In fact, I even gave you something with an h of x and asked you to guarantee something with an r. I mean, it's very close to the question that I gave you. Okay, you couldn't do C yet because we haven't done points of inflection yet. Okay, part B, but we will in next Wednesday, I think, or Monday. Show that g prime of 2 is equal to g prime of 5. Let's start with that. Show that g prime of 2 is equal to g prime of 5. Donovan, you soaking it in?
Osmosis.
Just be glad you're a junior. No, it's serious. Let's do this. G prime?
Wait, what is it then?
Okay. Show that g prime of 2 is equal to g prime of 5.
Oh, we're doing B?
Yeah, we're doing part B.
Okay.
Well, we have to find G.
Well, we have g. G is f of x. So what do we need?
So
F of X.
you need to know what the actual.
What's the X?
No, we don't. All we have to do is show that at g prime of 2 is equal to g prime of 5. There are ways of doing that symbolically. You don't have to have numbers to show that they're equal.
Wait,
Yes.
should it?
Chain rule. Go ahead. I'm sorry.
I guess.
Yeah, look. Well, don't guess. Look at it. It's a composition function. Okay. If I asked you to tell me what g prime of 2 is, what would you want to know before you could tell me that?
But F,
F.
but F.
No, that's you jumped.
But then if
Oh.
I would want to know too.
No. If somebody said, hey, tell me what g prime of 2 is, I'd say that's easy. Tell me what g prime of x is. You're going back too far.
But I
So you
still
don't
want to
need to know
know.
G.
Well, sure, but you need to know what g prime of x is, right? All right, so what is g prime of x?
F prime of F.
F prime of f of x times,
Oh, F of X.
no, the derivative of the inside times the derivative of the outside, inside unchanged. Well, we have the derivative of the outside, inside unchanged. What do we still need? The derivative of the inside. So it's f prime of x times f prime of x. Right? So now we need to know what g prime of 2 is. Okay?
F prime of F.
F prime of f of 2. Well, what's f of 2? 5. F prime of 5 times f prime of 2. Now let's find out what g prime of 5 is.
Oh, so we don't have to find the actual.
It's symbolic. That's exactly right. It is symbolic. It doesn't matter. You can still do it. If it's logical, if it makes logical sense, you can do it. All right, so now let's plug. We need f prime of f of 5. And what's f of 5? 2. So we need f prime of 2 times f prime of 5. Oh, look at that. That's exactly right, which means which means that they're equal.
Oh, that's the.
That's what it says. It says show that g prime of 2 is equal to g prime of 5.
Oh, so that wasn't like a.
Boom! They're the same.
Do we have to go through all?
Equals doesn't mean numerically equal, even though this would be numerically equal. Equal means having the same equation even. Yes, sir.
Shouldn't we have known that just by looking at the F of 2 and F of 5?
No, all this tells you, because f of 5 and f of 2 are not the same. Knowing the chain rule, yes, you should have just known it, but that would not be sufficient for the readers. When the reader, if you just said yes, they're equal.
So.
Yeah, that's a 50-50 guess. You didn't show it. It says show that g prime of 2 is equal to g prime of 5.
Is
Show. We just showed it. Yes.
Knowing that the slopes are equal to that point, does that tell you that it's differentiable, or are you just assuming that?
Well, we know it's differentiable because g is a function of f. It's f of x, right? And since f of x is twice differentiable, g of x is twice differentiable. Now, the second part says, use this result to explain why there must be a value k on the interval from 2 to 5, open interval from 2 to 5, such that g double prime of k is equal to 0. Not intermediate. Mean value theorem. G double prime of k equals 0. What is this? Can we now say this? You really should practice saying these things in language other than just their symbols. What does this mean? The derivative of the derivative at k equals 0. Okay? That's one way of saying it. Now let's say it another way. The second derivative of g at k equals 0. Good. What else? Yeah, I want you to say something that uses the phrase instantaneous rate of change.
Oh, the rate of change of the instantaneous. The rate of change of g at the instantaneous rate of change at k.
Very close. How about this? How about the instantaneous rate of change in the derivative of g at k is 0? No, not quotient rule. No. Well, what does the mean value theorem do? It matches two things. It says two things are equal. What two things? In general, what things are equal?
The average rate of change and
The average rate of change and the instantaneous rate of change are equal.
Where does it say this?
In the mean value theorem, it says something like this.
and both of those are the same, isn't that constant?
Not necessarily constant.
But
So what should this be equal to? Now it's g double prime of k. Yes, not g prime of c. Well, it says on the interval from 2 to 5. G prime of 5 minus g prime of 2 over 5 minus 2. And since g prime of 5 is equal to g prime of 2,
so it cancels out.
they cancel. That equals 0 over 3, which equals 0. So the average rate of change on the interval from 2 to 5, the average rate of change in g prime is 0. Therefore, somewhere on that interval, there has to be the instantaneous rate of change in g prime has to equal 0. It seems like you got it. I mean, halfway is good enough for now.
It's easy
Okay.
to follow usually.
Well, sure, but here's the thing is, I'm not going to be there. Well, you know what that means? You know what happens when that happens to me? This is what I say. My professor just led me through the maze. He took me from the beginning of the maze, we walked all the way through it, and I remember getting to the other side of the maze. That means somewhere in my brain is the way through that maze. I wish I had a computer, a textbook, some paper, a calculator to help me remember the way through the maze. Right? That's when I sit down with all that stuff and I tell everybody, don't talk to me. I got to figure something out here. Leave me alone. And I don't turn on the computer and I don't answer my texts. I just sit there with the stuff and I say, I made it through this maze. I'm going to make it again. And when I make it through this time, I'm going to remember how I got there. That's how you learn. That is learning. That, what I just said, that's learning. Okay? Learning is not doing it the first time. Learning is not having seen it done. Learning is not hearing from somebody how they think they thought someone else did it. Okay? Learning is exploring, doing it yourself, and redoing it, and redoing it, and redoing it until it is stuck in your brain and nothing can get it out. Okay? That's learning. That's how you know your family members. It's how you know your friends. You spent a lot of time with them. You know what I mean? You know, you don't know somebody, you don't learn somebody by hanging out with them one time. You know? So learning math and learning people is pretty much the same. It takes time and it takes, focus. Okay, we're now going to do we're going to do 2006. This is a good one. We're going to do 2006 Form B, Question 6, Part D. So 2006, AB 6, and it's Form B. Form B, and it's Part D we're going to do. If you look up there, it's this question. It says a car travels on a straight track during the time interval from 0 to 60 seconds. The car's velocity in feet per second and acceleration in feet per second, or feet per second squared, are continuous functions. Now, if acceleration is a continuous function, what does that say about velocity? It's continuous and differentiable. If the derivative is continuous, then that means that the function itself has a slope at every point, which means it's differentiable. Okay? So, we know that velocity is differentiable, acceleration may not be differentiable. Okay? The table above shows selected values of these functions. So there you have velocity and acceleration, and then you have time. Part D says, for the interval 0 to 60, must there be a time t when the acceleration is equal to 0? Justify your answer. Mean value theorem. Now, some people might consider using the intermediate value theorem. Some people might look at acceleration and try to use the intermediate value theorem. Can you use the intermediate value theorem up here? Nope. Why not? For acceleration to be 0... For acceleration to be 0 by the intermediate value theorem, right, that's exactly right. These are all positive numbers. There are no negative numbers up there. If one of them was negative, we could use the intermediate value theorem. Part D is asking us to use the mean value theorem. So should we go to acceleration? Velocity. It's asking us to show that the slope is 0 at some point. The slope of what? The slope of velocity. Is there any evidence in these numbers that the slope of velocity at some point is 0?
No.
50? No, that's velocity equals 0. At 50, acceleration is 4.
It can be because 0, 13, and 25, they kind of make it hard.
Yes. Look at 0, but ignore 15 for a minute. Just look at 0 and 25. Tell me about the average rate of change between 0 and 25. The average rate of change. It's 0.
I win.
Yep. Look, V of 25, which is negative 20. Well, we'll get to that in a second. V of 25 minus V of 0 over 25. V of 25 is equal to negative 20. V of 0 is equal to negative 20. Over 25, 0, the average rate of change in velocity is equal to 0. So the instantaneous rate of change in velocity, which we call... Now, what do we call the instantaneous rate of change in velocity? Acceleration, the derivative of velocity, which is acceleration. If the average rate of change in velocity is 0 on the interval from 0 to 25, then what must be true on the interval from 0 to 25? What's 0?
The slope?
Yes, the slope has to equal 0, or the acceleration has to equal 0 on that interval. And is the interval 0 to 25 on the interval from 0 to 60?
Yeah.
Yes, then part D, it says for the interval 0 to 60, must there be a time when acceleration is 0?
Yes.
Yes, in fact, it's not just from 0 to 60, it's somewhere between 0 and 25.
So what exactly would you write to justify it? Yes.
You would show this, this.
You don't have to like write any words, you can just write the word.
Well, this is a start, and then you would probably write something like velocity is continuous and differentiable on the interval from 0 to 25. The interval 0 to 25 is on the interval 0 to 60. And by the mean value theorem, the average, or since the average rate of change in velocity from 0 to 25 is 0, the mean value theorem says that somewhere on that interval, acceleration has to be equal to 0. That's it. Okay? All right, now let's do last one. Let's do 2009 Form B, question number 3, and we're going to do part C. We're just going to do part C. Read part C to yourself or out loud, I guess, if you want to, while I write this stuff up here. 2009 Form B, A, B. This is question 3, and we're going to do part C. Yes, sir.
Before you start,
Yeah, go ahead. I'm out of passes. If you want to write one or chance it, it's up to you.
This right there.
Okay.
Yeah, the woman in the hallway.
Okay, so a continuous function f is defined on the closed interval -4 to 6. Notice what's happening at 0.
Absolute maximum.
Yes, it is a maximum. Very good. And it's changing direction in what way? Is it changing smoothly?
no, it has a cusp.
So it's not a cusp, but a corner. Yep. So it is not differentiable at 0, right?
Right.
So if we're going to think about using the mean value theorem, we're not going to happen where? Where can we use the mean value theorem?
From 0 to 6.
We can use the mean value theorem from 0 to 6. Yep. All right, so this is,
That would have made the problems much easier if you were just like, nope, can't use it.
yeah, it would. And actually, there are some problems like that. In fact, it says, is there a value A on the interval from -4 to 6 for which the mean value theorem applied to the interval A to 6 guarantees a value C on the interval from A to 6 at which f prime of C equals 1/3. So we're looking for if there is an interval A to 6 where we can guarantee an instantaneous rate of change of 1/3. Can we guarantee an instantaneous rate of change of 1/3 on some interval that ends at 6 but starts at A? Okay. How far back could you go? To use the mean value theorem, how far back could you go? You can only go to 0, because before 0, because it's not differentiable, right? Okay? So it's got to be somewhere, but A has to be some value between 0 and 6. How would we calculate that value? How would I write it down? What do I have to write down? If I want to use the mean value theorem, what must be included in my answer? The average rate of change. That's right. And what would I start with? F of 6 minus f of A over 6 minus A. And this must equal what? 1/3. This has to be true, and now we have to find a value for A that will make this true. When you look at the graph. Somewhere between 4 and 6. I don't know about that, though. It's lower. 3 is lower than 4. So it can't be 2. Yeah, it's probably not 2 to 6.
4.5.
Okay, 4.5. We need a precise value here.
4.0.
If we go, okay, if we're at 6, look. By the way, you're allowed to draw on these papers when you're taking these tests. This is 2, this is 1, and it does this. Okay? Now, if it ends at 6, if it ends at 6, and we're guaranteeing a slope of 1/3, what can I draw from 6? What is this?
Another line.
A straight line. This is the slope of a secant line, right? Why don't we just draw a line from 6, from 6, 1, that has a slope of 1/3?
Oh, so you kind of make up a coordinate.
Yeah, so go down 1,
And over. Oh.
and oh my goodness, there it is.
So it's 3.
3.
That's kind of cheating.
This says it's not. It's not. Did you think that one was easy?
No.
I think it was.
I mean, I think it's easy now that you said
If I
that,
would've
but I
Yeah.
would have been like, well, let me just.
Look, if you're doing this, draw a line if you've got a graph. Draw a line with a slope of 1/3. It's going to cross over the graph. You are looking for a line that crosses over the graph somewhere, and it has a slope of 1/3 and ends at the point 1/6. You can even write the equation of the line if you wanted to. From here, it's going to go down 1, and back 3, it's going to have a y-intercept of -1, has a slope of 1/3 x minus 1. There you go. There's your line. Now find something that fits your graph. Okay? And here we know that a is going to be equal to 3. Yes, there is a value a on the interval from -4 to 6. It is 3. Okay? Because f of 3 is 0, and a is 3. 6 minus 0 is, f of 6 is 1. 1 minus 0 is 1. 6 minus 3 is 3. Okay? Does that make sense? All right, good. I felt like because the questions I give you on the quiz are going to be more like the AP exam questions and less like the textbook questions. Now, you might say, well then, Mr. Ryan, why in the world would you have us do all those problems in the textbook? Why do you think? Yeah, you need practice, you know. My job is not to teach you the AP exam, but to teach you to understand these theorems. What's that?
Are you recording?
Yes. Is that okay?
Yeah, I just forgot.
Oh, that's all right. Yeah, it's good. Okay. Now, we're done with these. Let's go on to the lesson for today. We're now going into section 4.3. What we are going to talk about in section 4.3. My title, if I were to retitle section 4.3, they titled it Connecting F prime and F double prime with the graph of F. Okay? This is what I would name it. Shapes of graphs. We are talking about the shapes of graphs. Graphs are geometric, right? Which means that they have shapes to them. They have curves, they have corners, straight lines, points. All of these things are geometric. Okay? So we're talking about shapes of graphs. But if I were to look at a function, an analytical function, f of x equals something cubed plus sine of x times e to the, I don't know, something crazy power. Okay? 1 over x power. I don't know. If I were to create some crazy function, is there some way that I can understand the shape of the graph of that function without actually graphing it? Well, that can help. Yeah, there are cues. There are things that you can look at that can help you understand its shape. Okay? What's that? The endpoint. Well, if there are endpoints. Okay? But what I mean is, I'm less concerned. All the things you guys are bringing up actually aren't shapes. They're more like end behavior. What I mean is this. Is it curving down or is it curving up? That's exactly right, and draw the graph. Or you can understand how to know the shapes of graphs, which is what this whole section is about. We're going to spend 3 days on it. 3 days, because it is critical that you understand how to recognize the shape of a graph. Now, a differentiable function has, I don't want to say differentiable. How about a function that doesn't have holes and jumps or corners? Has 8 basic shapes, and you can recognize all those shapes simply by looking at a circle. You can recognize all of those shapes simply by looking at a circle. Okay, here's what I'm going to do. I'm going to cut off some places on the circle. I'm going to put a cut here and a cut here. I'm going to put a cut here and a cut here. I'm going to put a cut here and here, and then I'm going to put a cut here and here. Okay? And here's what I want to show you you're looking at. You are looking at, I don't know how to number them, but 1, 2, 3, 4, 5, 6, 7, 8 basic shapes. Okay? Now the difficult ones are this shape and this shape. You're not going to see those very frequently. These are places where they have a vertical tangent line. So that's one possible shape of a graph, is a place where it has a vertical tangent line and it's either bowing to the left or bowing to the right. Those are not technical terms. Okay? Yes, 2 of them. One up here and one down here. Look at that, horizontal tangent line. What would you call this one? It's going up, then down. This is how would you characterize that in terms of extreme values? That's a maximum, right? A horizontal tangent line, but a maximum. This is a horizontal tangent line, but a minimum. That's right. That's exactly right. Do you see it? Okay. It's bowing. It's kind of down and then up. All right, and then here, tell me about the slope right here. Positive slope, okay, which means f prime of x is greater than 0. But what's happening to the slope? It's leveling off. Yes, no, that's right. It's going down. The slope is going down. The slope is decreasing. It's becoming flat. Becoming flat.
Like in the top of parabolas, how the slope is 0, does that happen on circles? Like, is the slope 0?
Yes, the slope up there is 0. Yep. Okay. Now, look at these other pieces. What about down here? Tell me about the slope down here. It's a positive slope, right? But it's getting, but it's getting steeper. This one's becoming flatter. This one's becoming steeper. So you can have positive slope steeper or positive slope flatter. Does that make sense? Okay. Last 2. Tell me if they look, tell me, based on what we just talked about, I want you to think about what's happening. Down here, tell me about the slope here. Negative slope, right? Negative slope, and it's flat. It's becoming flatter. Okay. What about up here? Negative slope. Now, by the way, this stuff that we're doing here is only for curvy functions. Okay. I'm going to show you what's happening here, though. Negative slope, and what's it becoming? It's becoming steeper, right? It's becoming steeper with a negative slope, right? Now, note that linear functions do not have any of these things. Yes, because linear functions, they have a positive slope. They're not getting steeper. They're not getting flatter. Or they have, that's right, constant slope. Or they have a negative slope, not getting steeper, not getting flatter. They're also not going to have a slope of 0. That one's not going to have a slope of 0. So linear functions are their own thing. Got it? But if it's a curvy function, these are the shapes that you will see on a curvy function. Either a vertical asymptote or a vertical tangent line, or a horizontal tangent line. Horizontal tangent line, that's a maximum. Horizontal tangent line, that's a minimum. Negative slope, that's becoming flatter, meaning it is approaching a slope of 0, or a negative slope that is not approaching a slope of 0, it's actually approaching a vertical, right? Then you've got positive slope that's approaching a slope of 0, and a positive slope that is not approaching a slope of 0, it's going away from a slope of 0. And now if we were to graph some crazy function that looked like this, you would see all of these shapes right on here. There's your maximum. There's your minimum. Look, yeah, what's happening right here? There's your negative slope getting steeper, but there's your negative slope that's getting flatter. Here's your positive slope that's getting steeper, and here's your positive slope that's getting flatter. Does that make sense? I'm going, over the next 2 days, I'm going to show you pretty much succinctly all of the analytical ways of identifying what the shape of your graph looks like. At any point, you can pick any x value, and by calculating two values from that x value, you will know exactly what is happening at that point. By calculating the derivative, which gives you the slope, and by calculating the second derivative, guess what the second derivative tells you? That's correct. That's exactly right. By calculating the first derivative and the second derivative at any point, you can know which one of these is going on. Is that cool? Okay. Well, you could just use the coordinates of the point to determine that. Yeah. Yes. Is the slope, the second derivative, and we're going to get to it on Monday. It's called concavity. It's called concavity. Yep, it's called concavity. We're going to get to that on Monday. Okay, so shapes of graphs. That's what we're going to be talking about. Today, what we're going to talk about in terms of shapes of graphs is called the first derivative test of relative minimums and maximums. This is it. In about 12 minutes. We can do this whole thing in 12 minutes. The first derivative test of relative minimums and relative maximums. Okay? So here's what I'm going to do. I'm going to draw two relative maximums on the board. Would you agree that that's a relative maximum right there? Would you agree that that's a relative maximum? Okay. This one is differentiable. This one is not differentiable. Doesn't really matter. Okay. It really doesn't. It doesn't. As long as it's continuous, it doesn't matter. Okay. I'm going to draw a relative minimum that's differentiable and a relative minimum that is not differentiable. Is this a relative minimum? Is this a relative minimum? Good. Okay. Now, without writing anything down, well, maybe I will. Well, let's talk first, then I'll write stuff down. What do we know is happening at this point right here? Yeah, the slope is, it's flatter. The slope is 0. It has a horizontal tangent line, right? So at that point, we're going to call that x equals c, and we know that f prime of c equals 0. At this point, we're going to say that that's x equals c. F prime of c is undefined, right? Okay. What about here? If we say that this is c at x equals c, f prime of c equals what? 0, horizontal tangent line. And here, as over there, if x equals c, f prime of c is undefined, right? Okay? We okay so far? Here's what I want to ask you. Tell me about the slope to the left of this maximum. Flattening, but that's right. I just want to know whether it's positive or negative or 0. Positive. The slope to the left of this point is positive, right? F prime of x is greater than 0. For values less than c. For x less than c. Right? What about on the right side of this maximum? Negative slope, right? For all values of x greater than c, f prime of x is less than 0. What about this relative maximum down here? Slope is positive on the left. And what is the slope on the right? Negative. So, for x values less than c, f prime of x is greater than 0. And for x values greater than c, f prime of x is less than 0. Without using mathy terms, is there any way, can anybody in this room describe basically what happens in this whole procedure of achieving a maximum? Is that a negative slope? Okay, we got to go from a positive slope to a negative slope. Now, what would happen if we went from a positive slope to a positive slope? That wouldn't be a maximum, right? So, what must be true in every case of a relative maximum? It always goes from a positive slope to a negative slope. So what do you really need to know? Do you need to know what the values are? You just need to know that on the left side has a positive slope, or that the derivative has a positive value, and that on the right side, the derivative has a negative value.
So that guarantees that it's going to cross the x-axis on the
Yep.
graph?
On the derivative, yes, that's correct. Okay? So and then that is the first derivative test. And then for minimums, it's the opposite. What's going on the left side? That's right. In order to have a minimum, you have to go from a negative derivative to a positive derivative. You have to go from a negative derivative to a positive derivative in order to have a minimum. So I'm going to show you it two ways. I'm going to show you it on a sign chart and on a graph. Let's say that we have some function, and when we take the derivative, we identify critical points at -7, -1, 4, and 13. These are critical points, which means that either the slope is undefined or the slope equals 0, right? And the slope on the left side here is negative, then positive, then positive, then negative, then positive. Okay? These are the values of the derivative, f prime of x. So the derivative is negative to the left of 7. Let me draw a picture of what the derivative might look like here. Excuse me, I shouldn't have put the 7. Okay, at -1, it's 0. At -7, it's 0. At 4, it's 0. And at 13, it's 0. It's positive here, negative between, positive between, positive between, and negative on the other side. Okay? That's a bounce. Sorry, that didn't cross. It's not supposed to have crossed over. Okay? Now, is this a minimum or a maximum? How do you know it's a minimum? The slope goes from negative to positive. That is a minimum. What is this? This is what we call a neither. The slope goes from positive to positive. What is this? A minimum? That's a maximum. The slope goes from positive to negative. And what do we got going on right here? That is a minimum. Without knowing any numbers. Did we have to plug in these numbers into a function? No. Without knowing what the output values are, we are able to identify whether they are minimums or maximums. Are we able to identify whether the -1 or two minimums? Are we able to identify whether -7 is lower than 13? No, we can't. We would need numerical information. But can we say that -7 is lower than -1? Yes, because what's happening between -7 and -1? Positive slope. The values are getting larger. Can we say that 4 is at a smaller value than -1? No. Look, what's happening between -1 and 4? Values are getting larger. That's right. Positive slope. Now looking at a graph, you know what? Let's now do one more. I think we can do one more. I'm going to make a new graph, one that's not related to this one. This is going to be the graph of the derivative. This is the derivative, f prime of x. Okay? Okay? This is going to be negative 5, this is going to be 1, that's going to be 4, and this is going to be 7. At negative 5, does f of x have a minimum or a maximum? And how do we determine a maximum? It is a minimum, isn't it? It's going from negative to positive. The slope is going from negative to positive. That means that we have a negative then a positive. Negative, 0, positive. What's happening at 1? Oh, sorry, did I do that wrong? I did that wrong. You just should have called me on that. Negative, then 0, then positive. Negative, 0, positive. There we go. That's what's happening there. So then this one is positive, 0, negative. Positive, 0, negative. That's a maximum. Maximum, minimum. What's going on at 4? Neither. That's a neither because we've got a negative, then 0, then negative. What's happening at 7? Think about it for a minute. It's a minimum. Negative, 0, positive. Negative, 0, positive. That's a minimum. That is the first derivative test of minimums and maximums. Yeah.
This is like all like graphs, like there's no actual numbers involved.
There are numbers in as much as, well, you might be given a function like what we're going to do on, I'm going to have some crazy functions where the numbers are not 7 and 4 and 1, where they're irrational numbers. Yeah. No. In class, where you're gonna calculate you're gonna graph something in your calculator and identify the zeros, and they're going to be at strange numbers, decimal numbers. Okay. It's not that there's no numbers, it's that we are not calculating the height of the graph. We are just identifying its zeros and then determining whether the slope is positive on the left or positive on the right, or negative on the left or negative on the right. All we care about is whether it's positive or negative. We care less about what the actual values are. Yes, please. Yeah, and there's also, wait, don't leave yet. You got another minute. Please also, there's also a video on identifying derivatives with your calculator. I figured since you're playing with your calculator, I'd throw one in that allows you to find out how to calculate the derivative with your calculator. And it's really easy. It's a very, very simple procedure. Yeah. Big test. Oh, yeah. Yes, That's ready to go.